So where are we right now? We've looked at inter-process communication in the context of remote procedure call. And we first saw the general idea of inter-process communication, which involves two processes talking to each other, exchanging messages through a queue. Okay, and the word process has been used for both threads and what we are calling processes here. So threads within a process or the processes themselves. And so that's why I say process slash thread. And if it's between threads, then the queue is not really distributed. But if the communication is between processes, then the queue is distributed. Okay. So we saw that idea, um, and then we saw that a port is just basically is this queue we are talking about. And in RPC, what you're exchanging is again messages, and the messages are requests for method invocations. Okay, so the sending process says, I want this particular method to be executed. The message goes to the receiving process, which goes and executes it. Okay. And usually it's built on top of data communication, which is what we look at next. Uh, and we saw Sun RPC was one simple way to do remote procedure call, which involved just the libraries. And then we saw in RMI something more fancy. Okay, and Gypsy was a variation of that. We also saw that messages, this data communication has a different flavor of message communication. So the message is not a request for data; it is a request for a value to be assigned to a variable. So you send some expression to be assigned that goes to the sending to the receiving process, which goes and actually assigns the expression to the variable that was intended. Okay. And in CSP, this is made very evident. Um, process P1 can say P2 exclamation mark E1 plus E2. So it's sending that expression to process P1. And P1 says, okay, whatever I get from process P2 should be assigned to the variable A. So that's CSP, and that was the foundation of the Go language we talked about. And if you just do an output stream print line E1 plus E2, that's also a way of doing the same thing. We're sending data across. And the other side just does instream.read. So again, asum is assigned E1 plus E2, but using a different interface. And it's this interface we're going to focus on. And it's this idea, remote assignment, that we're going to focus on, and this interface. So there's many ways to do remote assignment. And like we saw in the previous slide, there was this IO stream involved in the communication. So somehow remote assignment is associated with IO streams. And we're going to start with something very rudimentary, blocking input-output streams. So getC allows you to go and read a single character, read allows you to read a sequence of characters, putC allows you to write a single character, and write allows you to write a sequence of characters, and we'll focus mainly on getC and putC. Okay, so that's something that we learn basically in 101 courses. We'll try to understand what's going on underneath the hood, and that will motivate blocking IPC. And if you've done any sockets, and the ones who've done networking courses, you've seen those. And the ones who've done my programming language course have seen those. So they are a form of blocking IO. Okay, and they're provided in Unix and Java and other languages. And from there, we'll go to this non-blocking IPC and IO, which is a very modern thing for Java. It was created to build scalable servers, but in Unix, it's existed for a very long time. So we'll go to that. That's more complicated, so we'll go to that in the end. So let's look at blocking IO. Let's assume we have this object console. This is an object I've invented just to make things simple. And it has this putC and getC methods. PutC is a procedure, takes a character as an argument and outputs that. And getC is a function, and it returns a character. Okay. So somehow this is related to sockets, and this is related to blocking IPC. And let's try to understand how. Okay, so let's focus on getC. Why is getC uh, really doing a getC similar to communication through a port. Okay? And by a port, again, we mean a queue. Okay. So what's the queue involved in getC, and why is, and if there is a queue involved, then yes, we can say that it's related to a port. And here's a hint. When you do a getC, you can get the character, you can get characters that are typed subsequently, or they might be typed ahead, where the user has already typed the characters before the process got a chance to do getC, and getC will consume those typed characters that are typed ahead. Okay, so that's going to be my question. Where's the queue here, and why is getC similar to doing port communication? Okay, so raise your hands. Okay, so as we saw, as you guys mentioned, that there is essentially a user communicating with the CPU, if you will, and so the users represent, and the CPU can get ahead. Sorry, this user can get ahead, so we need to buffer the characters. So that's why we need a queue, and for this to be a strictly a producer-consumer problem, we need multiple threads. So there's clearly the reading thread, the thread that says, I want a character. Okay? The characters might have arrived earlier when that reading thread might not have even existed or might not have expressed its intention to read. So some thread must have um, gotten those characters. So how is the user represented? The user is represented uh, by the device, and the device goes and interrupts. Okay? And when it interrupts something in the CPU, some thread in the CPU must go and service the interrupt. So that is the interrupted thread. So it's not really as if the CPU device is the consumer and the CPU is the producer and the CPU is the consumer. The CPU is both the producer and consumer in the sense that the CPU gets the character from the device, and the thread that gets it is the interrupted thread, so that's running on the CPU, and it goes and puts it into a queue from which the thread that wants to read gets it. Okay? So we assume that for every interrupt, there's always some thread available to be interrupted. So there's something around, and so that's what this picture shows. That the interrupted thread produces the characters, and the reading thread consumes the characters. Okay? And that's for getC. So an input device interrupts a CPU. There might be more than one CPU, so I'm saying a CPU when it has new input. And the thread that is interrupted might be actually a user thread, a thread in the application processes running, or it might be a thread in the kernel. Okay, depends on the operating system, which takes the input from the device register and puts the queue in an input queue. Okay, so the input queue is a data structure maintained by the CPU, not known to the device. And the reading threads immediately or later consume the input from the queue. Okay, if the reading thread comes earlier, it gets blocked. Okay, waiting for the input to arrive, and when input arrives, it gets unblocked. And if the reading thread comes later, and put is just the dual of that. Now the consumer is the character is the producer is the thread that actually made the call, and um, it has to wait for the CPU for the device to finish outputting characters. It doesn't have to really wait, but the 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 there is some wait involved before all the characters appear in the output. Okay, so what it does is it just fills up the queue and goes its merry way, and the output device starts outputting characters. And after each character is output, it goes and interrupts and invokes some thread, an interrupted thread, which goes and takes the next character and goes and puts it in the output device, waits for and then another interrupt occurs, and then maybe the same interrupted thread or another interrupted thread goes and outputs the next character. So again, we have a queue with a producer and consumer. Okay, so After each output interrupt, some user kernel thread is on the CPU is interrupted, which takes the input from the output queue and which takes the output from the output queue actually, and puts it in the device register of the device, which causes the output. Okay. So I've used some familiar terms like CPU, which you guys should be all comfortable with. And I've used some terms that those of you who've not done operating systems, or even those of you who've done operating systems, might feel a little uncomfortable with. Okay, I guess this is just reiterating what I said earlier. So here are some of the buzzwords I've used. Kernel, well, we've all heard of kernel, but you may or may not understand what kernel really means. I've used the word interrupt. You should have studied some interrupts in 411, but I've heard that there's not that much focus on this. I've used the word device. I've used the word device register. So let's try to go and understand what these terms really are. Okay. So this slide took a long time to create. Okay. So let's see whether I can convey the ideas. So you see on the picture, main memory. Almost any consumer of computing has an idea what main memory is. It's bounded. It's not infinite. So we have L words here, or L plus 1 words actually. So there's memory and there's CPU. Um, and part of the memory is used for storing the data of processes, and part of it is used for operating system data structures, and part of the operating system is the kernel. So the blank area is available for the kernel. Okay, and how do the CPU and memory talk to each other? Again, this is something that you've studied, I'm sure, in depth in 411. They talk through a computer bus, a shared medium. And let's now introduce devices. Okay, so this is an input device, a keyboard, and the keyboard also talks to the CPU, and it has an input device, and devices have data associated with them, and the data associated with the devices are stored in memory in the devices, and the memory words in that memory are called device registers. Okay, so each device has a sequence of device registers, which is its device memory. Okay? So the data structures we're talking about reside both in main memory and device memory. And device memory is basically a sequence of device registers. Okay. So how do data get transferred between device registers and main memory? And now you see the resemblance to interprocess communication, where again you have multiple address spaces now in different processes, and data have to get transferred from one address space to the other. So it's good to look at this communication here to understand what's going on between devices and CPUs, and maybe that informs what happens between processes. Okay? So the question then is, how do we actually name these registers? Okay, we know how to name things in our main memory through memory addresses. How do we go and name the device registers? Okay, before we do that, let's go and see what happens. So this is an input device, and somebody input a character, and that character gets written in device memory, and this is where it got written. Okay, and now the question is, how does this character get transferred into our queue and into our main memory? Somehow this memory has to be named. Okay, so what really happens is that if you have a memory address space, memory address space is from 0 to n plus to n. Okay, so you have n plus 1 words there, and part of that address space addresses main memory, and part of that address space addresses device memory. Okay, so each device has associated with it an address in this memory, okay, or a sequence of addresses in this memory, and there's basically contiguous addresses. Okay, so this particular device might have L plus M and L plus N plus D1 being the lower and upper area in that memory. Okay, addresses of the lower and upper area. Okay. So now we can use our regular load instruction to go and load this memory. Okay. A load from this register to main memory. But the question is, how do we know when data are available? Okay, because we need some kind of some way to know that there's new data available. So there's a bit. So in, there's so your device memory holds data. It could be output data to be transferred to an output device. It could be data that came from an input device, and it also has status information. So this one is part of the status bit, and it says, "Hey, I have some new data that has not been consumed." Okay? So the data at this point, there can be some program that keeps polling this particular bit, and whenever it finds the bit is one, it can go and pull this data. Okay. Now this character A is intended for some user process, so maybe the user process itself can poll, except we don't allow that. Uh, we require we don't allow that because the user process runs in what's called the user mode. Okay, so the CPU has a mode bit that says which mode am I in? Am I in user mode or am I in kernel? So you have to go to kernel mode to execute that instruction. Okay, so let's go to kernel mode. And now I can go and say, address some area in the device memory and load that into main. Okay, so control transfers here. At this point, even though the character A is, so since the character has been read, the ready bit goes to 0, okay, saying that there's no more data available. And control returns, and we go back to user mode. Okay, so we need to go and transfer from user mode to kernel mode to go and access information in device memory. It's not as efficient as just transferring data from one part of main memory to another part of main memory, or transferring data from register to memory and vice versa. Okay, this is a costly operation. Okay. So now another thing that increases cost is this polling. To continuously poll this ready bit of each device is costly. So there is a way to do interrupts. Okay, so interrupts have to be enabled. So the device has to be told, hey, please interrupt. Okay, so now main memory not only has data and status information, it also has control information. So you can set this control bit to saying, okay, please interrupt. Now, just because a device wants to interrupt doesn't mean the CPU will honor the interrupt. So this is really saying, hey, device, send interrupts. There's also a bit in the CPU, in each CPU, that says, am I willing to receive interrupts? So if send interrupts is true and receive interrupts is true, then an interrupt gets posted. And you don't have to do polling. So what does it really mean for interrupt to get posted? Well, you always have to do some polling. So what the CPU does is it keeps polling each device's interrupt line to see whether it's high or not. So after every cycle, there's something called cycle stealing. It goes and quickly checks if there's an interrupt on high or not, signal high or not. If there is, it goes and services the interrupt. And that is more efficient than going to every device's memory and checking if the ready bit is on or not. Okay, so that's what happens. It goes and checks if the interrupt is on high or not. And if the interrupt is high, with each device, there's an interrupt handler associated. So with the keyboard device, there'll be one interrupt handler associated. With the screen device, there'll be another interrupt handler associated. So you will invoke the interrupt handler for that particular device. Okay. So let's say another character comes in, and now the interrupts are enabled, both in receiving and interrupts sending interrupts are enabled. So B gets written, the ready bit gets put on, and the interrupt bit goes high. That makes now the interrupt handler also executes in the kernel mode. So the mode goes from user to kernel, control transfers there, and it goes and executes while interrupt handler is being executed. It goes and disables interrupts. So now we see why it's important to have this particular bit on. Okay? So while interrupt is being executed, and think about why this happens. I'm going to ask that question later. Okay? So interrupts get disabled while this is executing, and the interrupt handler can now go and execute load L plus M plus 1. So we have this reddish memory and we have this green memory. Green memory is kernel memory, can be accessed only in the kernel mode. and then we have this red memory, which is the process. Okay, so we read the data, the ready bit goes to 0, and we go and set the interrupts to 1. Now that we've serviced the interrupt, we return from this, we go back to user mode, and we've actually done it. Okay. So what happens if there's more than one device? Well, you have another interrupt. We have a separate interrupt handler. So there's an issue about how you sort of keep time. You can imagine having a time device that keeps time and you keep polling it, but polling is expensive. So what typically happens is that you've got a real-time clock that interrupts every so on regularly at regular intervals, and depending on how many times the interrupt has occurred, uh, the CPU knows what time it is. Okay, so there's the clock handler also. Okay, so we've seen how interrupts cause um, um, control to transfer from user mode to kernel mode, and from user memory addresses to kernel memory addresses. Okay? There's another kind of event that can cause this to happen, and that is a trap. So traps get executed either involuntarily or voluntarily. So when you do a divide by 0, that is an error that's caught by the CPU, and it results in control going to the kernel mode, and a trap handler being executed with that particular kind of trap. Okay, and that trap handler can then go and do whatever it feels is right. Yeah, and it can then it can just go and invoke something that results in an exception handler being called in a programming language. Why are trap handlers important from communication point of view? Okay, so this is what's happening here, and you go back to user mode. So why are trap handlers important? Think about how getC actually going to be working. getC is executed by the user process, by a user thread in user mode. Okay? And it has to go and read data, and the data are in kernel memory. So to do that, it has to go to kernel mode somehow. So how does control transfer to kernel mode from getC? It goes and executes a special trap. Let's say the trap is 7. And that trap number says, I want to execute a system call. I want to execute a kernel call. Okay. So like any trap, it's associated with a trap handler. So execution goes to this trap. The trap handler, I should have had it go to kernel mode. Here we go. It goes to kernel mode, and then it goes to the trap handler and goes to the trap handler. And that trap handler for 7 says, this is a system call. Trap instruction can take data as an argument. And the data said, I want to do getC. So it says, among all the kernel calls I know about, you wanted to execute getC. So let me go and execute TTY getC, which is the proxy for getC in the kernel. And control transfers there. Okay. And it can now go and get data that was written by the interrupt routine. Okay, so the interrupt routine, which also executed in the kernel mode, wrote the data in some queue, and this can get the data and return it back to the user. Okay, so it goes back and it goes back to the user mode, and there's the stack that was involved had both a kernel part and a user part. So it can read the data gets transferred from the kernel part to the user part, and it gets the. Okay, so this gives you an idea of what's going on here. So now a question that I posed earlier, and let's try to answer this. Why disable CPU interrupts when executing interrupt handler? Okay, why was that important? Okay, so let's consider that question. Okay, so why disable CPU interrupts? To disallow another thread from being scheduled that accesses shared kernel data structures, okay, in general. And with what we've seen here is that we have this queue, and we want the queue to be consistent. We know that there's multiple instructions involved in consuming an item and moving the pointers. So we don't want another thread to be accessing this data structure. So how do we disallow other threads from accessing? Well, we can do so by making sure that no other thread is scheduled. Okay, if no other thread is scheduled, then no other thread can access. How do we make sure that no other thread is scheduled? We make sure that we who are accessing the interrupt routine don't get unscheduled, and scheduling happens either because we went and unblocked somebody, and we'll make sure we don't unblock anybody, or because a clock interrupt occurred and the CPU said, "Oh, your time quantum is over. Let's go and give control to somebody else." So we've disabled interrupts. That means we've disabled the clock handler, which means we've disabled rescheduling. Okay, and this will work quite well if there's only one CPU, and we'll get into, we'll see what happens when there are multiple CPUs. That will complicate matters. Okay, so that's what I'm saying here. Does not work for multiple processors, which allow multiple threads to execute concurrently. Okay. So so that's why we actually disable interrupts, and that's good, because if you didn't disable interrupts, even if it was not a critical code issue, we can imagine interrupts getting cascaded. Okay, while we are executing interrupts, another interrupt occurs, which gets put on the stack, and involves another thread being executed, perhaps, and so we could have the stacks overflow, and so that's yet another problem. Okay, but the main problem is that is to okay. So here's my next question: what happens when there are multiple processors? Should an interrupt be serviced by multiple or single processors? So think about what needs to happen on an interrupt. A device register has to get read. So do we want this? This is hopefully a simpler question. Do we want multiple handlers to be executed, or a single handler to be executed on a single CPU? Okay, so processing of interrupt needs to be done once, just like Andrew said. Okay, we need to transfer data once to memory, not multiple times to memory. So it's done by a single processor. So the more complicated question was, which was kind of harder to answer, so I didn't ask that, is that which processor then goes and services it? And that's a very good question. It could be something that the hardware chose. It could be something that that hardware allowed the OS to choose. It could be just, there could be no choice. It could be a well-defined protocol, and the protocol is that the first CPU that polls for the interrupt. Remember, the interrupt bit is polled, so the first CPU that polls for interrupt actually goes and services. Okay. So that's what would happen with multiple CPUs. So now we get into this original question: why disable interrupts when executing interrupt handler? To provide atomic execution. But what do we do when there are multiple CPUs? Okay, when you disable interrupts, you're disabling your interrupts, not everybody else's interrupts. So since there are multiple CPUs, there can be multiple threads, um, and these multiple threads can make kernel calls at the same time and access this shared data structure concurrently. So how to go and solve this problem? And I'll just give you guys the answer. And the answer is that we need support from the hardware. Okay, and we can't just rely on interrupts. So there is something called there are instructions that allow you to go and execute, that can be executed atomically, to go and read data. There's a test and set instruction. So you can go and have a flag that you poll, and the flag's value you go and test and set in one instruction. And if the flag says it's on, then we don't access the critical section, and if the flag is down, then we access the critical section. Okay, so we need some kind of data structure to so that we can access it atomically, and we can do that using this test and set instruction. Okay, so you often hear about test and set instructions in the context of multiple processes, and that's really too bad. We try to, in operating systems, get around polling. We have to poll to go and get interrupts. We have to poll the interrupt bit. Okay, maybe this will be simpler. So notice that I have getC and TTY getC. getC was executed in user mode. Okay? That's also provided by the OS, by the kernel. but it exists in user mode so that you can transfer control to it. And then you have TTY getC, which is executed in kernel mode. So why distinguish between getC and TTY getC? Why have this proxy call, the stub call getC that calls TTY getC? Why not just have one routine, and which basically says, why not just have one mode? Why do we have kernel and user mode? Okay, in fact, transferring control from user to kernel mode is expensive. So if we, okay, so it's for access control. And both the answers we got were correct answers. You know, people think of access control as a way to control malice. Um, and so that's one reason. But as Jason pointed out, it's also to prevent accidents. So we don't want to accidentally do something we don't want to do, and we don't want to maliciously do something we shouldn't be doing. Okay, so remember, look at this here. We want to read this data, but do we really want to allow user programs to set the interrupt bit and violate some consistency issues? Set the so there's uh, do we want controlled access to this so that one process can't reach somebody input intended for another process? With the kernel being an intermediary, we can have some intervention. Okay, so in general, we want, and also devices are a shared resource. So if one particular process just hogs a particular device, then another process may not be able to get access to it. So we want the operating system to provide fairness, to provide uh, to prevent malicious acts, and to do trusted things. Okay? So that's why we need both modes. Though I have worked on operating systems, there was one from Xerox that did not have this distinction, and when something failed, that was a personal computer, so they said, well, if you screw up, you're screwing yourself up. It's not a time sharing system. And when things failed, they failed very dramatically. The whole and the danger there was that you couldn't debug because you might have corrupted the debugger also. So what they used to do was, whenever things failed, they would copy the whole memory on disk, bring up the debugger, which would work with its own memory, gradually uh, would do its instructions and swap back to the user address space, and it was very inefficient. But when things did not go bad, it was very fast. Okay, so there are advantages of having no mode. Okay, so here's another question. What if multiple devices interrupt at the same time? Um, is there any well-defined way to determine which? So yeah, all devices are not equal. Some devices are more equal than others. And there's device priority, and how the devices are given priority is up to the OS. But the clock, the example we had, is given priority for two reasons that you guys mentioned. We don't want to lose track of time. Okay, that's very important. And if we don't service the clock interrupt quickly enough, we lose track. We might lose some interrupt. Okay, because servicing the keyboard input might take also more time. Okay, where servicing the clock interrupt might take less time. So we have to look at not only how frequently do interrupts arrive, how long they are required, how much time is required to service them, and what's more important. So if we lose a character, well, maybe it's not as bad as losing a clock tick. Okay, and more importantly, if we can probably service the clock tick fast enough, faster than the user can input characters. So if we don't go and service the input character fast enough, and then another character might be input, and we lose either the first one or the second one because the device register can't hold it, doesn't have a queue. So we're going to lose information in that case, only if another input event occurs before the first one is serviced. So hopefully, if we can do the faster ones and the more efficient ones earlier, we can ensure that we don't lose data from the. Okay. So there is a notion of interrupt priority. Okay, here's sort of another question, which is a really subtle question. Um, and I think I just give you the answer here, but let me see. So we know we've looked at the input device. Okay, every time there's a new character, the input device interrupts. When does the output device interrupt? Well, the output device interrupts when it's ready to consume the next character. That means it has gone and output a character successfully, and it says, I want more. So it goes and interrupts. That causes an interrupt routine to be executed, which goes and fetches the next character from the queue and puts it in the device register. Putting it in the device register causes the data to be transferred. When the transfer completes, the output device interrupts again. Okay, that's what happens there. So that all works fine when we have a sequence of characters to be output. But what about the output of the first character? So I've gone and printed out hello. Somehow that interrupt sequence started. So after H, E, L, L, O, interrupts occur. And after the O, the output device goes and interrupts. The interrupt routine goes and says, oh, I have nothing in the queue. So it does nothing. And then you go and then somebody says world. So for W to be output, an output interrupt has to occur, but the output interrupt occurs when the previous character has been output, right after the previous character has been output, and that occurred a long time ago and we did nothing. So how do we go and make sure that an interrupt occurs now? Okay, because we are relying on the interrupts to consume characters. Okay, and let me just give you the solution because it's kind of tricky, but this is something I actually faced when I wrote my first device driver. And I had to go to my advisor to say, hey, what do I do here? And he said, you do frobbing. This is what frobbing is. Uh, when it finds the output buffer empty, okay, the output interrupt routine disables interrupts. Okay, so the output interrupt routine is the one that is consuming characters from the buffer. And when it finds nothing there, it just disables interrupts. Now comes the printing of world. So TTY put C goes and puts world in the buffer, and it goes and sees that the interrupts are disabled. So after it's put P into the buffer, it goes and enables interrupts. Okay, so interrupts got disabled. Now it enables interrupts, and one of the side effects in many machines of enabling interrupts, output interrupts, is for the interrupt to be posted. Okay, so as soon as it goes and enables interrupts um, uh, after W, the interrupt cycle starts, and gradually the world gets output also. Okay, and this is going to be important. This form of signaling is going to be important. We need some way to signal to the output device to start outputting. Okay, and this is a old way of doing it, and it may still exist, or there might be newer instructions to do this. But this was the old way to do this. Okay, so it's 4:27. So we've done an important part of the lecture, and here is some text to explain all the stuff that we looked at graphically. I talked about one bus, but there's actually three buses. There's data bus, address bus, and control bus. Address bus for addresses, data bus for data, and control bus for control information, state control information, like which should interrupts be enabled or not. Okay. We've seen what device registers are. Okay, they are device memory that's accessed by memory addresses. And we don't, if we have device registers that are mapped to memory, then we don't need a special instruction for each device to read and write from that device. We've seen interrupts. We've seen that there is cycle stealing to actually service interrupts, and interrupts are associated with interrupt routines, and a device doesn't always interrupt. So it's interesting, why would you use polling? Why would you poll the ready bit to ever? Why won't you always do interrupts? And again, when I was writing my interrupt routines, I realized the need for that. So the person like me who's writing code can make mistakes, of course, And how do we track mistakes? By doing printouts. So if you're implementing putc and you want to debug putc, how do you do that? We run into this recursive problem, right? So what I'm writing is the interrupt based putc, and I use the kernel kputc, which was the polling putc, to debug my interrupt putc. Okay, so that was a lower layer, and that's why you do sometimes poll the ready bit and don't rely on interrupts. Okay, so you have control over which form of communication you're using. And again, this kind of polling occurs, or interrupt driven, event driven interaction occurs at higher level layers. Okay, and handlers execute in kernel mode. So we saw clocks also involve interrupts, though there is a time of day clock also that one can read, and the clocks have higher priority than other devices. And we talked about communication between data transfer between device registers and memory through the CPU, because that's closer to what we want to do in interprocessor communication. But there's also direct memory transfer, where you don't write things sequentially. You just take a chunk of data that's right from the network or from the disk and just write it to memory and then interrupt the device and say, here's the data. Okay. Or you go and transfer data from memory and then interrupt the device saying, oh, I've done the transfer. So multiple processors, each processor has a flag saying whether it wants to be interrupted or not. And like I said, you can choose, each interrupt is serviced by only a single processor. And we need atomicity when executing kernel routines in general and interrupt routines in particular. And if you're just talking of atomicity between threads on the same CPU, we just disable interrupts, and we make sure we don't go and reschedule some other thread. That's also important. Okay, we don't go and signal somebody. We don't notify somebody during that period. And when you have multiple processors, you have to do polling and use this test and set instruction that's provided like any other instruction is. And this is a term that people, I'm saying trap versus interrupt. Some people just say software interrupts versus hardware interrupts, but basically there are two kinds of events that can cause a kernel routine to be executed, to control to transfer from your um, current routine, and one is an event in the CPU. So a trap can occur because of some activity in the CPU which will allow control to transfer to some handler, or it could be because of an external device event, and that's an interrupt handler. Okay, so there are two handlers: trap handlers and interrupt handlers. Trap handlers executed in response to CPU events, and interrupt handlers are executed in response to device events. They both involve um, transfer from user mode to kernel mode. And unlike interrupts, trap handlers are not disabled or enabled. Okay? We are not talking about being already in a kernel routine and making sure no other kernel routine executes at the same time. So CPU in kernel mode has more power than in user mode. And this is very important. It's very important in the design of IPC mechanisms that we want to make sure that we have as few calls to the kernel as possible to execute some piece of functionality. So often things that could be executed as libraries get put in the kernel because the library code might involve multiple calls. And we'll see that example, I think, today. And address space is divided into process address space and kernel address space. Okay? And kernel address space consists of interrupt and trap handlers and other kernel data structures such as the queues that we were talking about, schedulers, virtual memory manager, and so forth. And what I've said so far didn't distinguish between kernel and OS. Uh, kernel is OS is providing us with a set of services, okay? And some of these services are implemented in the kernel, which means they require kernel mode. They require the higher privilege mode, and some services may not require the higher privilege mode, and those can be provided outside the kernel. And it's always, tricky what should go in the kernel, what shouldn't go in the kernel. And at one time, people said file managers used to be in the kernel as in Unix, and people tried to take it outside the kernel and then put it back in the kernel for efficiency reasons. You put it outside the kernel, then you can change it easily. So something like the shell is outside the kernel, and you can change it easily, and people have changed it easily. But at one time in Multics, it was in the kernel. So that's one example of service going from the kernel to user space. It's still provided by the operating system. It's just executes in the non-privileged state. And related to distribution, when you put things outside the kernel, you can put them in a server. And when you put something in the server, you can access it remotely. So a lot of distributed operating systems tend to be what are called microkernels, where they provide very little functionality in the kernel and most of the services outside, so that they can be accessed remotely. Okay, and this is related to the idea of a device driver. We often use the word device driver. And so what is a device driver? Let's look at two examples first. So when we were talking of input being handled, there was tty-getc, which was executed by getc, which was executed in the kernel. And then there was the interrupt routine that actually filled up the buffer that tty-getc was consuming. Okay, so tty-getc was executed by one thread, the user thread, and the interrupt routine was executed by the interrupt thread. Together, they were the device driver for that input device. So device driver is a piece of code that accesses data structures that basically beautifies the device into something, into a higher level abstraction. Okay? And it's got the upper half, which is the code that's executed in the user thread, and then there's a lower half that's executed by the interrupt routine. And you want to keep interrupt routines as efficient as possible. So you want to put as much functionality as possible in the upper half, which is executed in the user thread by a user thread in the kernel mode. Okay, so the user thread can execute in the kernel mode. And so the device drivers have upper and lower halves, and you see here what that means in terms of the input device and output device. Okay. So tty-putc is the upper half that is the producer. tty-getc is the upper half that is the consumer. And the input interrupt routine is the lower half that is the producer, and the output interrupt routine is the lower half that is the consumer. Okay. So let's look at that picture now. Okay. So tty-putc is the producer, and tty output routine is the consumer. And I'm using the word, okay, I actually I did a global substitution. So this should not be putc and getc, this should be put and get, which are put and get in queues. Okay, so I'll try to remember to do this later. So this is not putc and getc, it just threw me off first. So this is put and get in a queue. Okay, so the tty-putc was called in response to putc, and which goes and does a put in the output buffer, and the tty output routine does a get from the output. Okay. So upper half executes an application thread and queues printed characters. Lower half executes an interrupting thread, consumes next character, and writes it to device register. So like I said, device interrupts after output register written, cleared, and after interrupt posting enabled. So every time the interrupts are enabled, the device interrupts, as I mentioned earlier. And what happens in input? Again, this should be put. So tty input routine goes and puts into the buffer, and tty-getc does get from the buffer. Okay, so this is the producer, this is the consumer. Again, upper half executes an application thread, consumer characters blocks if buffer empty. So this is consumes characters and blocks if buffer is empty. That's what the upper half thread does. Lower half executes an interrupting thread, reads device registers, and puts in read buffer. Okay. Device interrupts each time a new character is written to register. So we know that with the queue might get full or empty, so we need some synchronization. So that's the next thing I want to address. How do we build synchronization? We've seen how to achieve mutual exclusion, right? We saw that we can disable interrupts. How do we do the signaling so that when we go from full buffer to non-full buffer, a consumer can consume uh, a producer can put a new character in, and when we go from empty to non-empty, sorry, non producer can put some new data in. Okay, we need that kind of events, those kind of events. So what do we do? Well, when we're talking of output, if the output buffer is full, then the application thread can block using some blocking mechanism provided by the kernel. Okay, and what about the lower half? Okay, we don't want an interrupt routine to block. Remember, the interrupt routine has disabled interrupts. If it blocks, those interrupts may never get enabled. Okay, so interrupt routines cannot block, and if it blocks, then device register might get full. If the TTY interrupt routine blocks, input device register will be overwritten as user enters new character. So, like I said, interrupt service is disabled while their interrupt routines are being executed. So, and clock interrupts also disabled. So that's a problem we have to wrestle with. Okay, that we can't have interrupt routines block because block routine can starve or delay threads. And that similarly, the output driver cannot block, and that fortunately is not a problem because of what I said earlier. After output in the last character, the interrupt routine will find output buffer empty. So we answered because we answered it. On finding empty output buffer, interrupt routine disables interrupt posting, and upper half enables interrupt posting when it writes to an empty buffer. So that synchronization we already saw, and there's no problem with the output routine not being able to block. Okay, we've seen this before. This causes a problem. TTY input routine cannot block if input buffer is full. So here's a user frantically typing away. The thread that wants to input things is stalled, is not ready to input a character, and the buffer is full. And the TTY input routines finds that, and what should it do? And it really can't do much. So typically what happens is it goes and tells the user, by maybe echoing a bell character, hey, don't type anymore because you will not be heard. Okay, so the main point here is, and we're going to see this later, we have a half synchronized bounded buffer. This is not a true bounded buffer between the devices. Producer waits but not consumer in the output case. Input case, consumer synchronized, consumer waits but not. Application threads can block, the interrupt routines can't block. Okay, and if we're implementing this using the Java array blocking queue, we can see why we need two sets of routines. You've seen the use of putc and take, and then the blocking calls, and then there's also add and get. Again, my global substitution changed all the gets to get C's. Okay, so this is really get, and so that's why something like an array blocking queue allows both fully synchronized bounded buffer and half synchronized bounded buffer. Okay, so to sort of summarize, as we are ending our class, we basically put C and get C together, define the blocking IO, and blocking IO involves a bounded buffer. Not a classic bounded buffer, but a bounded buffer that is half synchronized. Okay, and the bounded buffer has producers and consumers, and one of them, the producer for some devices, the producers are application threads and the consumers are interrupt routines, and for other kinds of devices it's the reverse. Okay, So that is I/O, and the next thing is to look at blocking I/O. Okay, and you see, and those of you who've seen sockets, you've seen that, but we'll just tie this to what we've seen with blocking I/O, and then we'll go to non-blocking. Okay. But while we still have this devices in our head, let's go and tie this to IPC more cleanly. So we see that in IPC where there's a bounded buffer, there's bounded buffer in device CPU communication. And essentially what we're doing is a remote assignment. We have some variables in the process, and those variables can be assigned essentially data in device registers, or the reverse can happen. Data in the process um, can be assigned to uh, device registers, which are essentially variables in the device registers. And you have two parties involved. You have two address spaces, the device address space and the memory address space. Even though two chunks of memory, they're part of the same address space in the sense that they are numbered in such a way that they're part of one contiguous piece of sequence of numbering. But they're really two disjoint address spaces. Each device has the memory in its physical in the physical device itself, not in the physical memory. Okay, they're just logically connected by the address space. So the next thing we look at next time is how we can model blocking IPC as really I/O and just see what we've learned there to inform what abstractions blocking IPC might have.